Okay, so next we have a common type of related rates problem that has to do with the movement of shadows. So I'll read you the question first, and then we'll talk about how we come up with the picture, and then how we are going to connect the values so that we can use related rates to help us solve the problem. So we have a 1.8 meter tall man. He's walking away from a 6 meter lamppost, and he's walking at a rate of 1.5 meters per second. The light at the top of the post creates a shadow in front of the man, and we want to figure out how fast the head of the shadow is moving along the ground. So here I've got my picture. You can see the lamppost is 6 meters. Again, this is not drawn to scale. The man is 1.8 meters, and there's rays of light that are casting downwards on an angle and creating a shadow in front of the man as he walks away from the pole. So right here, this point here is the head of the shadow, and we want to know how fast that point is moving along the ground as the man walks away from the lamppost. Okay, so what do we know here? So we know that this side right here is 6. We know that this height right here is 1.8. We know that the man is walking away from the lamppost at 1.5 meters per second. So there's a rate of change because we have meters per second, and meters represents distance and seconds represent time. So we have what I call dx by dt, because I defined x as being the distance between the lamppost and the man. So x is a changing value because the man is walking away from the lamppost, so it's a variable. And the rate of change of this distance, dx by dt, is equal to 1.5 meters per second. So we have our dx by dt, and we have our value x here. Now, what we want to focus on is how fast the head of the shadow is moving. So I introduced a second variable. We'll call that s, and it's the distance between the lamppost and the head of the shadow. So this distance right here is going to be s. So I have this is x, this is s, which means that the length of the shadow is going to be this entire distance, s minus x. So this is s minus x. Okay, and what we want to find is we're looking at how fast the head of the shadow is moving. So we're actually looking for ds by dt. So how far the shadow, or how fast the shadow head is moving. So it's distance in meters over time in seconds, so meters per second. So here's where we want to use some of our past knowledge, kind of thinking back to grade 10 when we worked with similar triangles. So if you look at our diagram, we have two right angle triangles within this picture. So we have the right angle triangle that's created by the lamppost, the ground, and the ray of light coming down. And we have, so we'll call that the big triangle. And then we have a smaller right angle triangle, which is created by the man and the shadow that he creates by that ray of light coming down. So we know that they're similar because they both have right angles, assuming with the assumptions that we're making here. The ray of light is hitting the ground at the same angle here and here. So because they have the same, all three angles, then the same in each of the triangles, we know that they're similar. And if we know that they're similar triangles, then that means that they're proportional. So, or sorry, the sides are proportional. So I know that the ratio of 6 to 1.8, so 6 on the big to 1.8 on the small, is going to be equal to the ratio of the whole side s on my big triangle and s minus x on my smaller triangle. So here I have a ratio that I've used the similar triangles created within my picture that allows me to investigate these variables. So I can start to see if there's a connection between, or I've created actually an equation that connects the s and the x. I also know, as I said earlier, that dx by dt is 1.5 meters per second, and I'm assuming that walking away from the lamppost is in the positive direction. Okay, so I'm going to use this similar triangle information or proportionality statement here as the equation that I'm going to use to relate the variables. So here's my equation here. And all I did is I just cross multiplied to get rid of the fractions. So I have 6 times s minus x times 1.8 times s. And then I just collected my like terms. And I now have an equation that says 4.5s is equal to 6x. So this is a nice equation that relates my two variables. And now I'm going to take the derivative of the equation as it relates to the variables with respect to time. So I'm going to find d by dt of 4.2s, and I'm going to make that equal to d by dt of 6x. So again, I'm going to use my chain rule here. So I have the derivative of 4.2s is 4.2, and then I'm going to take on my ds by dt, and I'm going to make that equal to the derivative of 6x, which is 6, and I'm going to take on my dx by dt. And now if I want to get my ds by dt by itself, which is what I'm looking for here, I'm just going to divide both sides by 4.2. So I have 6 times dx by dt over 4.2 is equal to ds by dt. And luckily, again, at this point, I have all of these values. I know that dx by dt is 1.5, so I can sub that in there, and I end up with a rate of change ds by dt equal to 15/7 meters per second. So we can conclude then that the head of the shadow is moving at a rate of 15/7 meters per second.